afternoon, everyone, and welcome to another webinars of ASTRAIOS as part of the ASTRAIOS project. We also welcome Dr. Raian, who will give us the presentation today or the webinar today. Thank you, Dr. Raian.
Thank you, Yola.
I would just want to say about the ASTRAIOS project. So ASTRAIOS is an EU-funded project, is working to identify the existing space-related education and training across Europe, project future demand for space skills from the European space industry, and identify actions to align and improve the career pathways into the sector. The project started in January 2023 and spans 3 years. We are now in the final year of the project. Now, this webinar is part of the ASTRAIOS webinar series. It will help the project to reach its goals of improving existing training material and developing new ones to fill the gap between the supply of and demand for space education and training courses. So today, the webinar, we will discuss the topic about artificial intelligence for integrating multiple types of remote sensing data for sustainability application. And thanks to our guest, Dr. Raian, who's an assistant professor at the Faculty of Geoinformation Science and Earth Observation (ITC) of the University of Twente, the Netherlands. Dr. Raian received the bachelor degree in computer science from the Federal University of Ouro Preto, Brazil, in 2008, and his master's degree in remote sensing and PhD degree in applied computing from the Brazilian National Institute for Space Research, INPE, in 2011 and 2020, respectively. His main expertise is the application of deep learning, machine learning, data mining, and other pattern recognition methods to geospatial data. Dr. Raian's research focuses on the development of AI-based model to automatically produce maps combining geospatial data of multiple types and nature. His main research line has been on developing automatic methods for mapping deforestation, monitoring the natural vegetation, mapping urban areas, as well as other applications. Dr. Raian also has collaborated with the official data producer in Brazil, INPE, Environmental Enforcement Agency, such as IPEMA, and others. Before joining ITC in 2020, Dr. Raian participated as a software engineer in the development of important open source geospatial platforms like the TerraLib library, the GIS TerraView, Terra modeling environment, and geographic data mining analysis, and the framework of DeepGeo. Okay. Thank you very much. And now we will give the floor to Dr. Raian. And and we also are excited about this topic.
Thank you very much, Yola. So thank you very much, everyone, for joining. I will start sharing my screen here. So welcome, everyone. Today, I will talk a little bit about the research that we have developed on using AI for integrating multiple types of remote sensing data mainly for sustainability applications. So basically, initially, why do we need AI? Every year we have had new sensors being developed and a lot of freely distributed data from different types and natures. And these many different sensors have produced dozens of terabytes every day, opening first an unprecedented opportunity to better understand our world, but also a great challenge of how can we process such a huge amount of data. And in parallel with that, a lot of applications and a lot of demands have appeared, increasing a lot the demand for extracting useful information from this image. One example of that is the United Nations Sustainable Development Goals, where there are 17 goals that the countries are targeting that focuses on improving the environment, improving people's lives, and so on. So besides that, like we need to understand and mitigate climate changes, monitor the biodiversity to mitigate the impact of our actions in the biodiversity. There is an increasing demand for smart cities as well, informing and enable good public policies require also a lot of data. And so many applications are demanding more and more useful data extracted from these images, from this raw data produced by the satellites. So we are living nowadays what we call the AI era, because given all that, with these increasing demands of data, a lot of investment have appeared in new algorithms and computational infrastructure for processing all those data as well. And together with that, we have had a lot of advancements in cloud computing, high performance computers and GPUs, and that have opened also unprecedented opportunities to perform analysis, for example, on a world scale and any type of scales that we want. So, but before that, we need to understand what is AI, what is machine learning that we are talking about. To understand that, we first need to understand how do we learn. Humans, we learn from past experiences, while the computers and the machines, they follow mostly instructions that are given by humans through mathematical and logical functions. Then, back in the 40s, some researchers started thinking, what if we could train the computers to learn from past data? Then we would manage to make the computers able to do tasks that humans do in an automatic way and much faster. And that's how the field of artificial intelligence started. So artificial intelligence is the field of computer science that is focused on developing machine learning and other algorithms that makes the computer able to perform in automatic way tasks that are usually performed by humans. So artificial intelligence is a broader field that focuses on the interactions of the computer with the environment, how the computer learns from that environment, but also how the computer takes actions based on that learning process. So the machine learning is a subfield from AI that focuses on making the making the computer learn from previous data. So we provide the knowledge through data to the computer, and the computer is able to, based on that, learn patterns and other things from the data. And inside machine learning, there are other specific classes of algorithms that are some that we will talk about today, that are the deep learning algorithms that focus mostly on how to represent that knowledge to make the computer able to learn, but also with that they are able to produce more powerful classifiers. Yeah. Okay, some applications of AI, it has been very much applied to autonomous vehicles, smart cities, games, economy, and also for automatic mapping and processing geospatial data. The first application we'll talk about is on monitoring forests. So the Brazilian National Institute for Space Research, INPE, has produced since 1988 estimates of deforestation rates and also monitoring on a near real time the deforestation in Brazil. It started with the Amazon in 1988, and later they expanded that to the whole country. And with that, programs like PRODES and the TER, they have played an important role in the development of the public policies and in the combat of the illegal deforestation. However, and those are the main reference on large-scale deforestation mapping nowadays. However, these methodologies, they are largely manual, based on visual analysis, which makes them very time-consuming and, of course, expensive. And by using machine learning to automate that, we can be able to dedicate all that specialized workforce to, instead of just analyzing the images, we could focus that workforce on analyzing the data and developing the policies itself. So based on that, one of the research that we have developed is on monitoring selective logging. These results that I will present for you is a paper that was submitted by a PhD student that I supervise, Xiniao Wang. This paper was submitted recently to Remote Sense of Environment and is under review. So selective logging is a type of deforestation that is usually the beginning of the forest degradation. And it's when people go and select just the best timbers, and they harvest just the best trees to sell the wood. And there is, despite like whenever we talk about that, we link that to illegal actions. There is also legal selective logging that is regulated by the government. In Brazil, in most of the states, it's regulated by IBAMA and by the Brazilian Forest Service. But it is estimated by Amazon, that is an NGO that works in Brazil, that almost 40%, if not the majority of the selective logging is not authorized. And a lot of that happens in protected areas, indigenous lands, which also threatens the traditional people. And it's usually the starting point for the forest degradation. The main monitoring system we have nowadays for selective logging is the TER as well from INPE. And the TER is the current reference system and the most accurate but it relies mostly on optical images and also on visual interpretation. And by relying on visual interpretation, again, it makes it quite time consuming. The TER nowadays relies on a big team of analysts that keep analyzing the images every day and producing daily alerts for the whole country. And since it relies on to make it able to have a near real-time detection and to produce fast alerts, it relies mostly on MODIS, CBERS, and Amazonia 1 satellites, which have CBERS and Amazonia 1 have a resolution of 54 and 64 meters spatial resolution, the AWFI sensor, and MODIS, it's up above 200 meters. So that generates also a bit of a limitation for the selective logging. And besides that, there is the fact that the whole Amazon is quite often fully covered by clouds, making it harder to monitor that with optical images. And therefore, we are investigating in this project, mapping the selective logging mostly with SAR images, but we are making tests also with optical images, but we are trying to rely mostly on SAR images to make algorithms also that are able to monitor the Amazon when there is a big cloud coverage. So in these were the first experiments that Xiniao did. And in this paper, she firstly developed the algorithm for this whole area here, that is a big area in the north of Mato Grosso, by getting the TER polygons, identifying the pixels of selective logging inside, and generating temporal series of that. After training that with these polygons, we generalized that to some protected units where we have data from the Brazilian Forest Service, where they are logged. So we have the GPS points with all the positions where the selective logging is happening. And also we made some tests on a bit of a larger scale on 2 municipalities in the state of Pará that are Paragominas and Feliz Natal. Sorry, one in Pará, the other in Mato Grosso here. So those are the two areas. So this was to test the transferability of the model. But then the first challenge here was that the TER data is mostly polygon data. So whenever there is a spatial pattern of selective logging, they draw a polygon all around the area that is affected by that selective logging. And they identify here two types of selective logging. One is called geometric selective logging, and the other, we call that disordered selective logging. Why this distinction? Because usually the geometric selective logging tends to be quite related to legal selective logging, to places where it is allowed to happen. And the disordered usually tend to be quite related to the illegal one. So that's why I'm making these distinctions. But then we had this problem of we have only polygons and we are performing classifications on the pixel level. Then after a lot of discussions with the TER team and with the team from INPE, because we have also a collaboration with INPE in this project through the supervision of Dr. Leila Fonseca, who is also supervising the work of Finial. And they told us that the main way that they use to highlight the selective logging is by working with the linear mixture model. When you compute the shadow and the soil and the vegetation fractions of the mixture model, by making color compositions of that, you can highlight quite well the pixels. Therefore, to be able to the pixels, since we knew that most of the pixels affected inside the polygons, they are for sure selective logging, we defined a rate, we defined the rate among the soil and vegetation fraction that we call it NDSVI, Normalized Difference Soil Vegetation Index, that highlighted those pixels and we could establish a threshold to generate our samples, controlled samples inside the TER polygons. And then we collected thousands of samples in all these polygons here in the north of Mato Grosso, and generated temporal series of SAR images for performing the classification. And then we were investigating the use of transformers for that. And the traditional transformer usually combines all the features of the samples in a temporal vector and analyze everything together. But by doing that, it loses a bit the relation among the features. There is another paper in the literature that they proposed the I transformer that do the opposite. They combine the feature vectors and they make analysis on the feature vectors. But that also generates a bit of a limitation on the temporal relation among the timestamps. Therefore, we combined the two of them in what we have called the interformer. And based on that, we generate a model that makes more powerful analysis on the space and the time. So here is a bit of the structure of the interformer and how it is done. And besides that, what we did also a dissimilar attention in which we force by making a negative rate of the attention, we force the model to convert into the dissimilarities instead of the similarities inside the tokens. And then for the input data, we used the SAR backscatter with the GLCM features to bring a bit of the spatial context, because since we are using punctual temporal series of each pixel, with the GLCM features, we bring a bit of the spatial context to that temporal series. And then we generated around 70,000 samples for training, test, and validation in the area 1, and then we tested the transferability for the areas 2 and 3 and 4. So the area 2, as I mentioned, we have the GPS points of where, with the location and the date where the trees were extracted, and we also compare it with the current state of the art in terms of automated system that are the RADD and the REDD plus AI that works with planet images. Then here a bit of the results. Here we did this experiments for comparing different models and selecting the best model, and our model managed to perform better than all the others in most of the metrics, with substantial improvement in the accuracies. So then, when doing the experiments with the GPS points, we identified that quite often we were having, if we analyze that on a pixel base, we were having quite a lot of problems in the accuracy, because whenever a tree is logged, most of the times the pixel that is affected is not the pixel related to that tree, but some pixels around that. And then we identified some buffers to compute that accuracy, and we considered the model accuracy if it identifies inside that buffer. Something like this. We defined that buffer on around 50 meters. That is more or less the area that is initially impacted by selective logging, and we computed the accuracy considering correct inside this buffer. And then for that, both with SAR and with SAR plus the GLCM, our model performed quite better. And the best results were with the GLCM when we bring a bit of the spatial context to the temporal series as well. So for the other areas, since we don't have GPS points, we have the detailed data. Besides the analysis on the pixel level, we did also the analysis on the polygon level, because for an operational system, usually the most important, we are not interested in identifying on the pixel level, but we are interested in identifying the region that is being affected by the selective logging. And in most of that, and then we compared our model with the amount of polygons that were detected by each of the other systems, comparing to the tech. Here's some visual examples. Our model could detect quite some similarities with the detailed area. And in terms of polygons, the polygons that were detected, we managed to detect around 94%, which was reasonably higher than the other approaches as well. For some of the models, we didn't manage to make the comparison because we didn't have the data available, and then we could not perform the analysis on the pixel level and the polygon level. And then for those municipalities, we could see here in those areas that most of the, most of the areas of selective logging were correctly detected by our model as well, and especially in comparison with the state of the art that works on optical images, we were quite close, but working with SAR images, which is usually quite more complex. So for the other experiments, here some examples as well of the comparison with the results from RADD, and also some visual representation of our results for some of the areas. And now, besides that, we are also working on some spatially explicit models that works on the temporal series, combining temporal transformers with vision transformers and performing the analysis together on space and time. The second application that I will present for you is a paper of another PhD that I co-supervised, PhD student, Paulo Silva Filho. He defended his PhD in the end of the last year, and this was one of the papers of his dissertation that was on mapping the nature of vegetation in the Brazilian Cerrado. So the Cerrado is the second largest biome in Brazil and has suffered a lot of pressure in terms of deforestation because it's one of the biggest agricultural expansion area in Brazil, and only 8.21% is protected of the whole biome is protected by conservation units. But it's a very important biome as well because it has a very rich biodiversity, and we estimate that around 50% of the biome has already been changed for anthropic use. So the vegetation of, why the complexity of this work? Because the vegetation of the Cerrado is quite complex. This is the typology of the vegetation that is divided in three bigger types that are the forest formations, savanna formations, and the grasslands. But in this typology, when you subdivide that, it reaches in the second level around 11 different types, and in the third level around 27 or 28 different types of vegetation. And this is quite confusing in the images and quite hard to map. So we developed some CNN-based models that combines SAR and optical images to try to map in different levels. In the first level, 3 classes, in the second level, 7 classes, to map several different areas of the nature of vegetation in the Cerrado. And then we developed 2 different networks, first one on one level, second one on the second level, and then we combined those 2 in a multi-branch CNN that first. Also, another issue here is that the reference that we used, that is also data produced by INPE through Terra class, is on 30 meters, and we were performing the classification on 10 meters with Sentinel-1 and 2. So to do that, we developed a model with 2 different outputs, one on 30 meters, but also super resolving that to 10 meters. And then we made some analysis of the uncertainties and of the accuracies on the 10 meters as well. We tested several different types of data fusion. First one on early fusion without feature adaptation, second with feature adaptation, and then also with middle fusion and late fusion. And here I think we can, the feature adaptation basically usually uses some convolutions for combining both data and trying to extract before entering to the network a decomposition and combining both networks. So, and also using wavelet-based multi-scale decomposition for that. So, basically, the model, we also did a explicit quantification, especially explicit quantification of the network, which brings for us the ability to point out the areas where the model is making mistakes with high confidence and making mistakes with low confidence. We calibrate that, and with that, those uncertainty maps, they also brings us insights of which areas needs to be analyzed by human inspection. So we define some thresholds on that uncertainty, and then we make that calibration with the incorrect uncertain and correct and uncertain. So here's some examples of these calibrated maps. So where the areas where we have higher uncertainties, we can bring that to the analysts to analyze, and the areas with lower uncertainties and higher accuracy, we can be sure that the model is performing well. So here's some other examples, and then with that threshold, we can highlight in any map by using this approach which areas that need more attention and which areas can be trusted by the model. So with that, for operational systems like the TER, PRODES, or Terra class, this allows us to semi-automate the processes and make the human task of inspecting the images much faster. So some of the examples here for each of the class of the accuracies that we got. And here we need to remember that some of those accuracies, they are a bit lower than they should be because of the comparison of 10 meters maps with the 30 meters resolution. So we believe, especially based on the analysis of the uncertainty maps and visual analysis of some maps, that this accuracy could be even higher if the reference was also on 10 meters, because especially on the borders, you have quite a lot of disagreement among the two maps. So here we skip a bit because this was some ablation studies that we did to define the models. And also here for the hierarchical model, where we could see that by performing the classification with the hierarchical models, we could have better classification and outperform the other methods. Another application as well that we will show quickly here is on estimating above ground biomass. This was MSc thesis that I supervised from UEE, and in her thesis she combined GEDI, Sentinel-2, and Sentinel-1 in their original resolutions without having to perform previous fusion to estimate above ground biomass for big areas in the Amazon. So the reason here is GEDI produces some maps on above ground biomass, but the maps they produce, GEDI is a sparse LiDAR, is a volumetric LiDAR that measures the canopy structure of the trees, but it performs that measurements on sparse ways, which makes it difficult to compute the maps because we have a gap of 60 meters up along track and 600 meters across track. So the usual methods for doing that is by combining GEDI with TandemX for estimating the above ground biomass. However, TandemX is not freely available everywhere, and also by just interpolating that, you lose a bit of accuracy. Therefore, we use deep learning to combine that with Sentinel-1 mostly, and also by including Sentinel-2, we managed to improve even a bit more. So we basically performed the training and the validation in these 21 areas across the whole Amazon, with those 2 test sites in red being selected only for test. The others, all of them were we performed training, test, and validation on them, and these 2 ones only for test was for analyzing the transferability of the model on space. So basically here, some of the metrics that we managed to reach quite high R-squares with around 71 when combining the three types of data. And just here, one point, the reference maps that we used were from a paper from Nature, from the team from UNIP, in which they flew some LiDAR in several regions of the Amazon, and then they extrapolated the models for the rest of the Amazon. But their maps are produced in 250 meters, and here we used those. Let me show here. Yeah, we used those 250 meters maps to produce our maps also in 150 meters. I don't remember if it was 150 or 160. I think 160 meters. And with that, when we analyze the comparison among the labels and the models, we could see that in several areas, you could look for this river here, for example, that we managed, even though we were kind of super resolving the maps, we managed to capture in more details the features in higher resolution. So, which means that we can generate quite accurate maps on higher resolution using these lower resolution labels. And here, one thing that I forgot to mention, the reason why we are performing these studies on estimating the above ground biomass is because this is a very important data to understand the carbon life cycle, in which by estimating accurately the biomass, when we analyze the other maps of nature vegetation, deforestation, and so on, we can estimate how much carbon stock we have in each type of vegetation, but also we can better estimate how much carbon we are emitting by deforestation or any other type of land use change. And I will pass through another example quickly. This is a bit older. It's from my PhD. This is a paper from 5 years ago, and my PhD thesis as well. But is still relevant because this method is still quite comparable with the state of the art nowadays. And basically here we performed large-scale analysis on mapping the deforested areas across some areas in the Amazon and in the Cerrado. So the main challenge here is that automating these maps for these huge areas, the Amazon has 4.2 million square kilometers, and only the Brazilian Amazon, and the Cerrado around 2 million. This generates huge amounts of data that makes it quite hard for processing. And also, so this is one of the problems that we face for fully automating the deforestation detection systems. So basically here, we developed two types of fusion networks. One, spatial temporal fusion with a middle fusion where we combine the two images before the decoder, and the other one we combine before the encoder of the network. So we first executed in two smaller scale areas, one in the Brazilian Amazon with around 110,000 square kilometers, with around the experiments we had around 27 gigabytes of data, and the other one with 130,000 square kilometers in the Brazilian Cerrado, which we had a data set of around 25 gigabytes of data. And after that, we tried to scale that up to the whole extension of the Pará state, which has around 1.25 million square kilometers, which generated for us a data set of around 300 gigabytes of data, which you can imagine that is quite challenging for processing. So some of the results in the smaller scale in the Amazon, just a visual analysis. And here, these were also the comparisons that we did for developing the model and selecting which loss function we had, because we had to use loss functions. We tried the soft dice loss function and also the weighted cross entropy. And we could see that with the weighted cross entropy, we managed to reach a little bit higher because it balanced a little bit the imbalance between the classes. So it could handle a bit better than the dice loss. And also, when you look here to the accuracies in the deforestation itself, we could see that we also managed to reach something close to 95, 94% for that smaller area. And here, another issue that we could see is, first, the cloud mask that we used had a lot of false positives, and we could see that our model predicted actually better than the ground truth that was the cloud mask from Landsat. Second, like PRODIS, once the area is mapped, they don't look back to that area, which makes that some areas that regrow are not looked back, but in the image for the model, in some areas they can look, some very old areas, they can look like forest again. This area, for example, is an area that was deforested in 2007, and when training the models for 2018, these areas, they were in PRODIS, in our ground truth, they were classified as deforestation because they are not primary forest anymore, but our model managed to delineate quite well. So this shows us that our model actually may have an accuracy even higher than the numbers that we show because of these differences in the methodology of mapping generates some noise, some kind of noises for the model. So when we transferred that to the Cerrado, we managed also, the Cerrado is a much more complex area to map the deforestation, the suppression of natural vegetation, and we managed still to keep accuracies around 92% for the not deforestation area and around 88 to 90% for the deforestation class. And also having a higher precision than the recall shows that we are actually having more false negatives than false positives, which for deforestation detection is quite important. So then when scaling up for the whole para-state, this is the ground truth and our prediction. And when we analyze the metrics, we also manage it for the whole extension of para-state to keep F1 scores of close to 93%. So we manage it even for a very high and complex area to keep a very high accuracy. And another issue that we found that were masking those accuracies are PRODIS has a third class that is called non-forest, that those are the areas that are composed of non-forest formations. They are natural vegetation or naturally exposed soil that are actually not exactly deforestation, but they confuse quite a lot the model because they look spectrally and spatially in some cases look like the deforestation. This area here, for example, is a naturally exposed soil in the top of a hill. So this also shows that if we mask those areas, we could also have even more reliable maps and higher accuracies. So I will just mention other applications that we have worked. We have also worked on the fusion of SAR and optical for producing deforestation maps in several MSc theses and other projects. This is another example that I will not enter in details. This paper we produced on mapping illegal mining for the whole Brazil, with a bigger focus in the Amazon, because there is where the biggest amount of the illegal mining happens in Brazil. But I will not enter in detail because this was already presented in ASTRAIOS webinar by my colleague now, Luis Cortinez, who was also a PhD student that I had the opportunity to supervise during his internship here. If you want to watch his webinar, is in this one, in this link here that you can access to the QR code, but it's also in ASTRAIOS YouTube page. Another research that we are working on that is related to that is on using AI for mapping slums on a global scale. This is the project ID Atlas. I will also not enter in details on this one, just mentioned, because it was also presented by my colleague, Professor Claudio Percelo, in the last webinar. I will show you also the video with the QR code for that. But basically, one interesting thing in this project is that in Argentina, for example, it has helped us to identify several informal settlements that were before not included in their database and now have been included. And now we are also participating in a project with the team from Argentina on mapping other cities in the country there. And we are also investing on the scaling up for at least 200 cities around the world. So if you want more details, you can check our website, idatlas.eu, or you can also watch the webinar of Professor Percelo in YouTube, in our YouTube channel. And okay, coming to closing the presentation, some of the challenges that we face nowadays are on the lack of training data sets, the lack of good reference data for that. And this paper is still, the paper that made these two analyses here is from 2019, but the findings that they found are still valid nowadays, where the biggest lack are on, we have quite a lot of data set with very high resolution images for example, mapping buildings or roads, but we have a lack of data sets in many other applications. And with that, because of that, data-centric AI has become also a big hot topic nowadays that not only our group, but a lot of people have invested a lot in improving the quality of the classification through improving the quality of the training data. And this brings us to also this, that is, we always, whenever we are working with artificial intelligence, the models they learn from the data. So this makes it very important to focus on the quality of the data even more than the quantity of the data. Many people tend to think mostly about the quantity. Oh, I need millions of samples. How many samples do I need? So usually I like to say, like, instead of thinking about how much samples do you need, think about how good are the samples you have. Like how much that samples you have cover with the minimum noise possible, all the variability that you have. And also, when producing, because we have a lot of land use, land cover maps, these are just some examples of that available nowadays. And when we think about producing training data with the land use, land cover maps, the land use, land cover maps, they are usually a picture of a whole period. If you are generating samples with one single images, that can generate noises that you need to deal with that are, for example, from a deforestation that didn't happen in the date of that images yet, or many other types of noises. So with that, I close, and also I would like to use this opportunity to make a tribute to a researcher that unfortunately we lost in the beginning of the month, Dr. Dalton Valeriano from INPE. We called him in Brazil the visionary of the forest, and he was very important for the field. He was one of the main minds behind the Brazilian deforestation programs, the Brazilian deforestation monitoring programs, one of the main minds, one of the main responsibles for designing all that programs that we have nowadays in Brazil. And for me, besides great inspiration, he helped me a lot. I got a lot of knowledge from him, and was also a great friend that I had thankfully the opportunity to work with and to coexist with him. So thank you very much, everyone. And I'd like to bring back the floor to Yola for questions.
Okay, thank you, Raian, for this very exciting presentation. And I'm sorry about also Professor. So let's start. We have a couple of questions. I will read them. The first question, did ground truthing involve also additional advanced equipment or just simple GPS-based surveying? And there's a follow-up question, but let's maybe start with this question. I think you presented
the selective logging. For the selective logging, no, we only had the GPS points. I'll bring it here back. We had the GPS points from the Brazilian Forest Server, by the Brazilian Forest Service. And we had also some, here is an example of some of those points. And we had also the polygons from the TER, from which we generated the main ground truth for training, which is data like this. But we didn't do any field survey. We are relying on the knowledge from the team from the TER in Brazil, and also from the Brazilian Forest Service. We had extensive conversations with them to understand the problem and also to better understand their data.
Thank you. Also, other question, it's not follow-up, but other question, did you also have issue with shadows or only clouds? Any thoughts on that? How best to handle, like in mountain terrains?
Yes, the shadow, actually, I see that as even a bigger problem than a cloud, because usually most of the cloud masks, they struggle on getting the shadow. And these, whenever you are generating, for example, a cloud-free composite, those shadows is where it will generate a lot of noises as well, artifacts in the image. So the cloud usually is the shadow is usually quite a big issue as well. I would say the best ways to deal with that are through getting samples also in those places, because sometimes you have places where, despite the shadow, there is a little bit of reflectance on the targets there. Or also in some cases, like in the application of the deforestation detection here, what we did, we got the cloud mask and we inserted the cloud mask as another class. So these are the best ways of dealing with that. But I would say sample is the key. Try to get samples on those areas and get better quality samples.
Thank you. Another question. Thank you for a very interesting presentation and well done on the result achieved. Do you think that the ESA biomass mission will be a game changer for your analysis of the Amazonian preventions or degradation? And what features would you like to see from biomass radar images that could improve your model?
I would say absolutely, because if you look, we worked with we worked with Sentinel-1, which is actually Band C. Since Band C doesn't have a good penetration in the canopy, especially when we talk about areas of dense forest formation like the Amazon. With the Band B, you have a much deeper penetration. You can get much more information, structural information about the vegetation. So I think it will indeed be a game changer on biomass estimation because of working with Band B. And in terms of which features, I confess I'm not an expert in SAR. So I would say the best polarimetric data we can have with the more variety of polarizations with, for example, 4 polarizations instead of 2. I think this would help, but I'm not expert in SAR, so it's hard to tell.
Thank you very much. Maybe last question. What channels are used to communicate the results to senior decision makers? And in your opinion, how can we enhance the influence of research outcomes on policy and decision making?
Sorry, I didn't.
So what channels are used to communicate the results of the research to senior decision makers? And in your opinion, how can we enhance the influence of research outcomes on policy and decision making?
I would start first with the last part. I think for enhancing the impact of the research, we need to work as close as possible with the local stakeholders, but with the biggest variety possible of stakeholders, like work with the government, but also work with NGOs and work also, for example, we have done that quite well in the ID Atlas project, in which we are working closely together with community leaders. We are working with communities associations, with NGOs, but also with governments and with the institutions that are responsible for politicizing on those areas. So I think this is the best way of generating the impact, increasing the impact for research. In terms of the deforestation, for example, I have collaborated with INPE, with IBAMA, and with several other institutions, also with some NGOs. And so I think this is the best way, try to collaborate with the biggest amount of stakeholders possible. In terms of which channel, I think the person probably, I don't know if you mean the types of maps or information. I didn't understand what's the meaning of the channels.
Communicate with the decision makers
Okay.
Governments, like from the government side, how is there collaboration? But I think you also mentioned that the government already understand the outcomes of the results, and they try to take it into consideration as well for decision making, maybe prevention or protection of the forest in the different projects.
Yeah, I think like this is first try to collaborate with the local stakeholders, but also of course in research that doesn't involve privacy of people, as much as possible make the data public. The data of your research should always be public, and like if you don't manage to collaborate with local stakeholders able to use the data for public policy, bring it to the media, social media, and try to make as much noise as you can with that data. I think this is if you don't manage to, the best way is always to collaborate with local stakeholders. But if they are not open to collaboration, making noise through media, through making the data public, and show the data to the world, I think this is the other best way of doing that.
Thank you very much, Dr. Raian. I think it's the end of our webinar. Thank you again for these very interesting projects, and also we thank the people who attended the webinar. This webinar it's recorded and we also will publish on the ASTRAIOS YouTube channel. We also stay tuned for another webinar. Thank you again, and I wish you a nice afternoon.
Thank you, everyone.
Thank you.
Nice to meet
Bye.
you.
See you.
Bye.